Now let us see the mechanism of electrophilic substitution reactions. I mean the regular one or the general one. Okay. See the reactant. Let me show a general one. Now this reactant with EA, from which we get electrophile. Now the reactant is attacking the electrophile and then the A minus goes off. Now this is our step 1. See, in the first step itself we get this, which is of course called a sigma complex. We'll tell you in detail about all these when we go for the properties like halogenation, nitration, sulfonation, etc. But for now, you just see what all is happening overall. Now from this, again the A minus comes into picture, and this A minus takes out hydrogen without the bonded pair, and then this enters into the ring. Okay, then we get the final product. Yes, electrophile is attached. This is the final product, and then this HE. Now when the same thing is shown in the form of a free energy diagram, let me take the free energy diagram to show the same 2 steps. A graph is plotted between delta G versus a reaction coordinate or the progress of the reaction. Okay. Now in this case, we get this type of curves. Now look at this. This refers to the first step, which is in fact slow, because the height of the energy barrier is more. We have already seen such a thing even earlier also. First step is slow because it has a greater height of the energy barrier. This is your first step. Then coming to the second step. Second step is little faster because the height of the energy barrier is less. You know that these are reactants, and this is a product, right? You can show it this way. So anyway, this is the difference between delta H. Okay. So this is how we can show the free energy diagram. Right. Now let us apply the same to different types of electrophilic substitution reactions. We have a total of 5: halogenation, nitration, sulfonation, then Friedel-Crafts reactions, alkylation, and acylation. Okay, we'll go for them one by one. Let us first see halogenation. What is halogenation? See, in this, a weaker electrophile H plus is replaced by X plus, nothing but halonium ion. In fact, this is the electrophile in halogenation. Okay. Now let me first give you some examples for halogenation, then we'll go for the mechanism. See, when benzene, yes, reacts with chlorine, in the presence of a Lewis acid, aluminum chloride, or ferric chloride. Let us take a hydrogen out. Remove a hydrogen along with the chlorine. It's not the authentic mechanism, but only to write the product you can use this. A chlorine here, that of course is chlorobenzene, then HCl. Even with bromine also. A similar reaction happens to give a bromobenzene. Right? Of course, HBr. Then iodination. Little bit interesting. See, in this case, the reaction is slow, at the same time reversible. Very important. Take a hydrogen out. You get iodobenzene plus, of course, HI. Now, we know that this reaction is reversible and we need to prevent the backward reaction. See, for that sake, we use an oxidizing agent. Now, this oxidizing agent removes Hi by oxidizing it into iodine. Now, what are the oxidizing agents regularly used? We have nitric acid, iodic acid, mercuric oxide. Okay. These are the oxidizing agents which convert Hi into iodine to prevent the backward reaction. Okay. That is halogenation. Let us see the mechanism now. We'll take all the three steps. The first one is generation of electrophile. Yes. Okay. Now in the first step, let us take bromine along with ferric bromide. You know, ferric bromide is a Lewis acid, right? Lewis acid is an electron pair acceptor. And you know, this Lewis acid is simply used for the generation of electrophile. Very important. Why is Lewis acid used? Okay. Now, let us do this. The pair of electron is given into the vacant orbital of iron, upon which, say, we get this bromine, which is still having two lone pairs, then the FeBr. Now looking at this, bromine has got just 6 electrons around it as against 7 what it has to have. So let me put a positive charge on this. Iron earlier had only 3 bonds, nothing but 6 electrons, but now it has 7 electrons. 1 electron more than what it has to have. So a minus charge. Okay. Now, we have almost generated the electrophile. Let us see how benzene attacks the electrophile. Come on. See, in this step, which is of course a slow step, nothing but the rate determining step. This one attacks the bromine. Of course, this bromine will now become Br plus. That is your electrophile. Then immediately this bond goes to the positive charge, right? You can actually show it this way also. If you want, you can take it here, a negative charge, a positive charge. Now the negative will attack, sorry, not that. The negative will attack this. Even this way also is okay. In fact, the thing what I have written in the beginning says the same. Okay, look at what happens. Okay. Then here anyway we have a hydrogen. We'll now get a bromine, but at the same time we get a positive charge here. Right? Now, the resonance part. Again, a simple mechanism. See here, all three can be given in this format, in the form of a resonance hybrid. You can actually see that the positive charge is moving from here to here. Come on, let us show it this way. Right? Of course, the H and Br. Now this is called resonance hybrid. And these are called sigma complexes or arenium ions. All are aromatic. Okay. Now here the thing that is eliminated is FeBr3 minus and the other bromine. Nothing but FeBr4 minus. Okay. So this is how the sigma complexes are formed. Now in the last step, we will be considering this to form the end product. Of course, you can take any of the three. Let me take one of the sigma complexes, taking the first one itself. And let me actually consider the thing that is being eliminated in the first step. Br, FeBr3 minus. This Br was okay. with all 7 electrons, what it has to have. Now, say this bromine will just take out the hydrogen without the bonded pair, and the bond comes here, I mean to the rescue of the positive charge, right? But this step occurs very fast. You get your final product. Plus, of course, the FeBr3 Lewis acid, which was just used for the generation of electrophile, then HBr. So the overall, I mean the final products are bromobenzene and the HBr, right? And here, let me actually tell you one very important point. See, in this case, no kinetic isotopic effect is observed. See, because we don't have the cleavage of carbon-hydrogen bond in the rate determining step, no kinetic isotopic effect is observed. See, we have the breaking or the cleavage of the carbon-hydrogen bond in the first step, not in the rate determining step. So, we don't observe kinetic isotopic effect. That means even if you go for deuterium or tritium in place of hydrogen, that doesn't make any difference as far as the rate is concerned. Very important. Now the second one, nitration. In fact, the mechanisms will all be similar with small changes. See, in this case, a weaker electrophile H plus is replaced by NO2 plus. See, this is nitronium ion. Okay. Now, what is nitration mixture? You know, a mixture of concentrated nitric acid and concentrated sulfuric acid in 1:1 ratio is nitration mixture, right? Let me give you the reaction. See, when benzene is treated with the nitration mixture, look at the role of sulfuric acid. Of course, you'll come to know about the role of sulfuric acid in detail when we go for the mechanism. But this is very important. You know, when you carry out this reaction at a temperature below 60, then only you get nitrobenzene. Yes. important thing is temperature has to be below 60. What if the temperature is above 60? See, if the temperature is maintained at above 60, we get metadinitrobenzene. Okay. That means exhaustive nitration occurs. So this is basic nitration. Let us see the mechanism. The first step, generation of electrophile. Now see the role of sulfuric acid. See, for convenience, let us take it this way. It of course helps us in forming the electrophile. So this is our sulfuric acid, and then consider nitric acid. With the formal charges. Now, as and when the lone pair is given to H hydrogen, H plus, this will just go off. See, we are still left with a pair of electron at oxygen, a positive charge because it has only 5 electrons. Then of course this. See, we also get HSO4 minus. Look at this. Now, what happens is, as and when this comes, no doubt the positive charge is neutralized. But even this positive charge is also neutralized, and it goes off in the form of water. We get our electrophile. But see, as and when this bond goes towards positive charge on oxygen, nitrogen will again get a positive charge. That is, of course, the electrophile that we are going to get. So this is nitronium ion, the electrophile for nitration. Now go for the second step. Formation of sigma complexes. Similar. Look at this. Now this NO2 plus comes into picture. This step is of course a slow, rate determining step. Look at this. Okay. Now the same thing. The positive charge is anyway neutralized. But now we get a positive charge here, forming the sigma complexes as usual. Now this one. See, these are the sigma complexes. No big difference from what we have seen in case of halogenation. Now, these all can be given in the form of this resonance hybrid. This circling, I mean, this thing actually refers to the thing that the positive charge can be on any of the two ortho positions, and of course the para position. So this is our resonance hybrid, a mix of all different possibilities. In fact, resonance hybrid is the actual structure, right? Sigma complexes or arenium ions, right? Coming to the last step, the formation of end product. Take one of the sigma complexes. As usual, let me take the first one. Of course, any of the three can be taken. Now, the thing that we have eliminated in the first step, HSO4 minus comes into picture. That's it. So this step is in fact fast, wherein you got the cleavage of carbon-hydrogen bond. Observe this. Right? That's it. You got the final product, nitrobenzene. Coming to note, the important note here is, even here also we don't have kinetic isotopic effect. A very important point. As I said, even in this also, the carbon-hydrogen bond is getting broken. I mean, it's undergoing cleavage in the fast step, not in the rate determining step, right? So this is the mechanism of nitration.